Awesome.
Yep.
Okay, so thank you guys for having us come up here and present. We're going to talk about unconventional reservoir development, especially how it applies to the Utica and Marcellus shales. So let's get into it. So we're going to talk about early modeling and development, as well as the pricing influx, different generational designs we've seen, as well as some economic modeling, and then, of course, how do we apply machine learning to what we're actually developing up here in the Northeast. So let's get into the early modeling and development. So essentially, when we're developing proper oil and gas assets, we want to make sure that we have a good reservoir model. So what does that consist of? Typically, we'll look at the reserve estimation, the transient analysis data with it, the production forecasting, and then once we kind of put those data points together, we kind of get together as a group and say, okay, does our reservoir look good? Does this make sense to us? Does our economics make sense to us? If that's yes, obviously we start initiating development, and we'll start tweaking data. So you can kind of see in this model here, this is something that Eclipse does. Essentially what they do is they do what I just said in the geology and reservoir section. Then as they drill, complete, and produce their wells, essentially the cycle goes in a circle. So obviously what you're doing is you're developing these wells, you're building more data points. So as you build more data points, your reservoir model gets more and more predictive, hence where the machine learning comes in. So looking at the reserve modeling, the first thing we typically do is we want to learn about our reservoir. So does our reservoir have heterogeneity? What's our cores look like? As you can see in this picture, what's our PVT properties? So once we take those PVT properties, we can essentially figure out what our initial geophysics are. So the things you've learned early on in petroleum engineering: porosity, water saturation, area, height, formation volume factor, pore pressure, so on and so forth. And then you can kind of apply those to figure out what your reserves are, what your fracture modeling will look like, as well as what your drive mechanisms are, as well as your mineralogy. So using those data points, we can essentially figure out, okay, how much gas do we have in place? So we use this when we're developing. We typically use like a pilot well to get all of this data, and it's static data. So essentially what we use is our triple combo and the points I just talked about. And we look for free gas, dissolved gas, and absorbed gas up here in the Northeast. So you can kind of see examples of what we did here in homework 1. That was kind of the idea, to understand how that works. Essentially, we assume some sort of recovery factor in the beginning, but as we get more data and we kind of see what our wells are doing, we can better adjust that to get better estimates. So another thing we use, this is from SPE 177-293, and from my friends in natural gas engineering who shared some slides with me. This is transient analysis, especially with rate. It's this applicability here. So essentially what we're doing is we're agitating a well in transient analysis and studying its responses. Only in this case, the well is actually flowing. So instead of shutting a well in like we typically do, this is when it's producing. So essentially what our responses are is our reservoir information. So that's our permeability, our skin, P star, P average. In unconventional reservoirs specifically, we experience really long flows, periods of transient flow. So what we've been able to determine is that in this particular area that we're typically dealing with linear flow model, because as you can see, we have a half slope line. So what we do is we use the Wattenberger model to basically estimate flow capacity. So using these two equations here, we essentially can figure out what our permeability is. That's what A square root of K is. It's basically K8 or KH. And then we essentially take our formula here and we can modify some of the parameters we find with our slope and use this original gas in place equation, which is before boundary, but it's basically a good comparison tool to say, okay, are we on the right track? Some other things we use this for, we can obviously figure out our permeability and kind of compare with completions, how it operates. So this was actually pretty revolutionary when this came out. This kind of gave us an idea of, okay, do we need to do more sand loading? You know, what different things can we adjust to have better performance? And obviously another case study here, you can see where they're able to basically history match and figure out what our production is going to be from that data. Another thing that we can do is then production forecasting. So essentially what we do is we build decline curves, and we also curve fit, which I'll talk about that a little bit later. So essentially we had our initial declines, ARPs, exponential, hyperbolic, like you learned in class. But what we learned is that with shale, we have really quick declines, so we have to modify these curves to be able to handle it. That's the purpose of the modified hyperbolic and or the multi-segment. So essentially what we look at is instantaneous production, P factor, the terminal decline, and then the initial decline. With that,
all right, so starting with pricing and flux, we're going to go ahead, Jay. Look at the chart on the right, which shows the natural gas price over the last 20 years. And as you can see, from 2002 to about 2008, we had a large increase in the price of natural gas. And so starting in 2002, our shale assets accounted for 1.6% of the total U.S. gas production. That increased in 2005 to 4.6, and then again to 23.1% in 2010. And as of 2017, according to the U.S. Energy Information Administration, it was up to 66% of the U.S. or the total U.S. gas production. So now moving on to Henry's Hub. This is a natural gas pipeline distribution hub located in Erath, which is on the coast of Louisiana, in a high pipeline activity area. So this hub sets the base price, is basically the price benchmark for the rest of the United States. And according to this case down here on the bottom right, this was taken in 2012. The price influx throughout the United States was about 50 cents per million BTUs. And so Henry's Hub has 9 interstate pipelines and 4 intrastate pipelines that gather there. And their prices are based off of regional market conditions, transportation costs, supply, demand, and transportation capacity. And unfortunately, in the Northeast, there's a lack of pipeline output, so the operators are forced to send their natural gas to Henry's Hub. And with that, I'm going to send it back to Jay.
Different generational designs. So essentially, when we started developing this, we had different generations that showed different characteristics. So what the landing point was of our wells, the lateral length of our wells, the stage spacing, as well as the completions design, which was your proppant loading, your rate, your chemical concentration. Particularly in the Utica and Marcellus, we're on generation 3 right now, soon to be 4, probably here in the next few years. So first generation was our initial pilots and first development wells. We had pretty small lateral lengths at this point. You're looking at like 3,000 to 5,000 feet. Spacing was relatively large. 250 is kind of generally what we said here, but I also remember seeing like wells that had 500-foot spacing. So as you can imagine, not very good specifications on your stage spacing. We then had cross-link gel chem design. Essentially, we used that to help kind of load our proppant in the hole. We ran 1,600 to 1,700 pound per foot here, and we had lower EURs. Second generation, we switched to more of a hybrid system because we realized that guar and FR could basically carry the same sand rate that we needed. So we essentially switched to that method, and it was a lot cheaper. We then went to 80 to 90 barrel a minute. Sand kind of dropped off a little bit. Spacing obviously got smaller. Our lateral lengths got a little bit longer, which we still use some of these lengths today, and the EURs got better. Third gen, which is what we're on now, it kind of ranges more from 7,000 to 20,000 foot in your more extreme case. Higher rates being 80 to 90 barrel a minute. 100% slick water now. We basically have these high polymer friction reducers that can act just as well as guar and basically minimize formation damage. And essentially, that's what we kind of use now. Proppant loading is heavier, 2,300 to 2,800 pound per foot. Stage spacing was smaller, 150 to 200. This shows the greatest EOR so far, according to case studies. And then lower pressure declines is also something we've seen. So you can see my group member attached kind of a graph of what this looks like. You can kind of see the different sand designs here and the stage spacing and the declines. If you want to know more about this, you can ask me later on. I'm actually in the process of writing a paper on this. So let's talk about my section, the economic modeling and optimal forecasting. So essentially, we're going to talk about the different parameters of an economic model very quickly, and then kind of how we apply everything we've talked about so far to a case study. So essentially, the first thing we need to understand is what type of NRI do we have and what working interest do we have. So essentially, NRI basically dictates how much income that you're going to get as a company. Specifically, your royalty interest part is very unique in the United States because we actually lease from landowners that own the mineral rights, whereas in like other countries, the government actually owns it. When you're doing these royalties, your interest must equal 100%. You probably can't really see here, but you can see there's a lot of landowners in here, so you have to add all of those percentages up. Then we do modeling on all of those to understand kind of the income and how the money's being distributed, basically. Then we can start talking about CapEx, which is your capital expenditure costs. What does that consist of? As a company, that can be anything. Production wells, central gathering facilities, pipelines, injection wells, can be anything. Specifically in our case, Utica and Marcellus wells, you typically see costs from $8 million to $15 million with your superlaterals in that particular case. So the next thing we talk about is the OPEX, which is your operating expenses. That consists of your fixed lifting costs, so like your stone, mow the grass. Variable lifting, which is kind of on a per MCF or per barrel basis, so that would be like your water production, for example. gathering and compression, so the cost for your midstream, obviously, to be able to gather that gas or that hydrocarbon, and then obviously compression costs. If your line pressures are too low, you're going to have to compress your hydrocarbons to get it up to line pressure. Processing, so if your gas is extremely rich, you're going to have to pay costs to basically break it down into profitable hydrocarbons. And then transportation for your interstate transport. Then once we do all that, we can essentially figure out our NPVs and IRRs. So NPV is obviously net present value. It's the sum of our cash flows and the discount. We typically run before tax and after tax. Obviously, if before tax looks not very good, obviously it's probably not going to look good after tax. So that's kind of why we run the two. But obviously, if before tax looks good, you want to make sure it looks good after taxes. And that's part of what we do. So you got your corporate, ad valorem, and severance taxes. Internal rate of return is basically when your discount rate gives your NPV value of 0. Obviously, you want both of those terminologies to be greater than 0. Well, which one do we choose? Well, are you a long-term company? That's kind of more of an NPV. Or if you're more of a flip and sell, that's more of an IRR type. That also dictates how quickly you're going to develop. So shrinkage, something we deal with up here in the Northeast. If you remember in thermodynamics, we had Joule-Thomson effect, where essentially we had lots of pressure cuts and temperature. You have liquid dropout. So essentially we have to deal with shrinkage. So that's part of your shrinkage, as well as how much you use in the field to power your equipment, as well as transport. That you can calculate that from your NGLs, your PVT samples, plant efficiency, as well as we actually look at it with the raw data to kind of compare. Obviously, if we could crack everything on pad, we would, but it's pretty dangerous, so we don't. So that's kind of the limitations we reach. You also have gravity, as well as in the Utica specifically. I've seen pretty high shrinkage, 25 to 35%. BTUs also dictates it, so that's the amount of energy to raise water 1 degree. So the more rich the gas, the higher the BTU. We also calculate that from the same parameters, PVT sample, plant efficiency. So with that, your curve fitting, so essentially what you're doing is once you start developing your field, you have to go back in when you're producing your wells and make sure, okay, does your type curves match what your production is? So that's what you do with your curve fitting. You essentially adjust your curves to make sure they're accurate. And this is something production engineers do and reservoir engineers do all the time. Probably at least once or twice a month, not every week. So with general history, I kind of talked about this a little bit. You can kind of see where our developments went. Technologies such as ARES, at-risk, Harmony, and machine learning have kind of helped us advance this reservoir specifically. So let's talk about a case study. So this was a particular case study. This is SPE 191-468. So this testing was initiated in 2016. We call it the Deep Dry Utica. There's several operators in this area that have acreage, EQT, CNX, Range, Stone at the time, now EQT acreage. So essentially, basically what we did here in this particular case study, what they did was they took an old log from the 1970s from Peoples Gas, and it was a pilot log. They reprocessed that log, looked at what the initial gas in place was, like we already talked about earlier. Then they built those parameters into an MEM, basically kind of isopac models you can see there. And then they said, okay, let's run economics to develop this. Does it make sense? Okay, it makes sense. So let's see what the probability is that we'll actually get that. So that's what they did with this Monte Carlo simulation you can see up there. So they said, okay, looks good. So let's drill a pilot well. So they drilled their first pilot well about 5 miles away. They used the Ohio type curves to kind of compare because it's a similar formation. When they decided to bring this well online, as you can see here, it was actually above type curve. So they're like, awesome, we have more reserves, right? So they decided to, let's rerun Monte Carlo, let's rerun economics to see what it looks like. So they did the same thing. It looked good. So they said, okay, let's be sure. Let's drill a couple of delineation wells, which are these wells right here. So they ran those wells. Again, those flowed over type curve. So they bumped them up to 3.8 BCF per thousand and ran their economics, and it made sense. So they decided, okay, let's run full development. So that's a great example of using the different techniques and how it can be an advantage to you in industry. And so with that, I'm going to hand it off to talk about machine learning.
So the applicability of machine learning and better optimization in reservoir development. So a brief and quick information about the machine learning. In 1959, American computer science named Arthur Samuel, he created and theorized the idea of machine learning. He used that term to describe the capacity of computer and to educate themselves and on how to solve the task Machine learning has since then Machine learning has since then evolved into a very significant concept that's seen as the artificial intelligence, which known as AI. So the process of the machine learning contains of these four parts, which is collecting relative data, developing a deep learning training model, and developing an optimized objective function. And the last one is creating an optimization algorithm. So the purpose of the machine learning is to get high accurate prediction of the production and iterate the previous good production databases and locate sweet spots in a field for the optimal productivity. Now moving into the integration of reservoir development into machine learning. A good example where we can see this method used is in the development of the Bakken Shale petroleum system, which is an unconventional reservoir oil reserve. This method is contained about these four parts that I will go through each one step by step. So the first stage, data collection and analysis. The following parameters were collected: the perforation length, stage count, NSL, MVV, and NVF, maximum injection rate, and maximum injection pressure, and so on. In the second stage, developing an optimized objective function. In this method, the relative pairs of the inputs were compared using the Pearson correlation coefficient. And we can see the formula here. Second, to improve the prediction, we used three different methods. They are RF, RFE, and SSL1. And the third method, developing a training model using deep learning machine. Here we have a structure of a deep learning algorithm. Basically, it contains of three parts: the input layer, hidden layers, and the output layer. The final stage of creating an optimization algorithm. In this final stage, final input parameters were used to create this predictive model. And we used the total thickness, MVV, depth, porosity, stage count, MVF, NSL, and water saturation. Now moving to the proper optimization of economics and reservoir development. Machine learning can also be applied in the optimization of reservoir to produce the maximum quantities of oil and gas at the lowest possible cost. And to achieve that, we have to predict a predictive model, and we need two main factors. These two main factors: the first factor, total depletion rate of the reservoir; the second factor, geographical distribution of the reservoir production capacity. And these two factors lead to using some different variables, as we can see them in this integration. These are some of the variables that we used on the previous integration. For example, price of petroleum, capital cost, operating cost, petroleum production, and so on. Now, finally, the future productivity and economic improvements. Machine learning predictive properties have the advantage of predicting future productivity. So, for example, we can optimize that how to get better economic returns, and how to analyze time rate decline and the need of the successful prediction. Finally, the improvements in the future productivity and financial viability. Thank you for your attention. Please feel free to ask any questions.